Okay, so the last video we have discussed what's a vector space, right? So we take a set. Okay, the set contains elements like v1, v2, dot dot dot, vn. Okay, and then along with this set I have to define an operator called vector addition. Okay, and then a scalar multiplication. And after I define these rules along with this set, I have to check whether certain axioms are being satisfied. Okay, if those axioms are being satisfied, then I call this set along with this operation as a vector space, and each element in this vector space is a vector. Okay, now in this video what we're going to do is can I call a function, okay, function like f of x is equal to x square or sine of x. Okay, can we call such functions as a vector? Okay, so that's the question we are going to answer. Okay, so in that case, first thing what I should do, I have to define a set. Okay, so I have to define a set. Maybe I will erase these things. Some set of functions. Okay, I'm going to take a set of functions. And then I have to define an operator, the plus operator and scalar multiplication operator. Okay, the plus operator I can just define the normal operators addition sense. Okay, so for example, say this is f1 and this is f2, then f1 of x plus f2 of x is just going to be equal to x square plus sine x. Okay, so the normal vector addition. And scalar multiplication, scalar into a function is equal to, for example, 5 is the scalar which we are going to use, then f of x 5 into f of x is, say f1 of x is nothing but 5 x square. Okay, so that's how I am defining the scalar multiplication. Okay, and then if we check the axioms, okay, and if I have chosen the set such that it satisfies all the axioms, then I'm okay. Okay, and it will work. Okay, maybe I will give an example. Okay, I will take a small set, say 1. Okay, just a constant, then x, then x square. Okay, just a set with 3 elements. Now this is how I am defining the vector addition and the scalar multiplication. Now if I add any two vectors, okay, if I add any two vectors, will it be within the system? Okay, for example, I say I add x square and then take another vector 1, okay, and that results in x square plus 1, which is not an element in this set. Okay, and therefore this set along with this operation does not satisfy this axiom. Okay, so which means in the vector space, okay, in the vector space, if I have all possible functions, okay, say not just these things, um, all possible functions, all functions. So in that case it will satisfy. Okay, so these axioms will be satisfied. Okay, so from that sense we can say a function as a vector. Okay, but there is a problem to consider everything mathematically, because whenever we imagine a vector we put an arrow mark. Okay, so that's how we imagine to have a geometrical intuition about vector. Okay, that's true, but when we have to deal with a vector in a higher dimension like 5 dimension or 100 dimension, okay, at that time it will be very difficult for us to have a vector which is having an arrow. Okay, so at that time maybe it will be somewhat useful for us to imagine a vector, okay, as a function. Okay, so one way of representing a vector is a finite dimension vector is a column matrix, right? So now let's say this is some A, okay, and this is some B. Okay, and the way I am going to represent this column matrix is follows. Okay, so for example this is n dimension. Okay, now I'm going to do is I'm going to divide this A to B as n discrete points. Okay, and at each point I'm going to put the value of, or I'm going to mark at each point I'm going to mark the value of the entry in this column vector. Okay, so for example say it's a 3-dimension vector and it's 3 2 6. Okay, so in that case I will put 3 over here, 2 over here, and 6. Okay, so that's one way of imagining a vector. Okay, so that's a 3-dimension vector, and if it's going to be a 4-dimension vector, maybe I will have a vector representation. Okay, so in that manner I can have a 100-dimension vector. So if it's going to be a 100-dimension vector, then who knows, it's going to be something like this. Okay, now the function is nothing but an infinite dimension vector. Okay, which means for every real number between A and B there is an entry. Okay, there is an entry. So in that manner if we imagine, then we can understand this function. Okay, this function as a vector. Okay, so right, so that's how you can imagine or you can give a geometrical intuition while you're considering function as a vector. Okay, now if it's going to be a vector, then what you could do is we do some operations using vector. For example, dot product. Okay, so what do we mean by dot product in a vector? But before that dot product I will show what do we mean by a vector addition. Okay, So vector addition is nothing but, for example, this is f1 and there's another function f2. Okay, vector addition is nothing but, so addition of this point plus this point is equal to, I don't know, maybe this point. Okay, addition of this plus this is equal to somewhere this. So like that you are adding. Okay, so that's the vector addition. Even in the representation of column vector, you will add this element with this element, right? So you can associate this column vector with this function. Okay, right. Now what we are going to do is we are going to define inner product, okay, or a scalar product or a dot product. So in dot product what we do is we'll take two column vectors and put one column vector as a row vector and we will multiply. Okay, so while we multiply, what we do, we'll multiply first entry to the first entry of the first entry of this vector to the first entry of that vector plus second entry of this vector to the second entry of that vector, and like that we will do, right? Similarly, what we will do here is, for example, I'm going to take a dot product of this two functions f1 of x and f2 of x. Okay, so once again let me give this picture. So this is f1 of x and that's f2 of x. Okay, so this is f2 and this is f1. Okay, so I'm going to multiply each entry. Okay, which means say that is at some x. Okay, which means f1 of x into f2 of x. Okay, and then what am I doing? I am summing it. Okay, so I have to sum, but it's a continuous function, so instead of summing, what I'm going to do is I'm going to integrate. Okay, so this is a and that's b, so I'm going to integrate from a to b dx. Okay, so this is how we do the inner product. Okay, this will be very useful. And now can we do a cross product? No, we can't do cross product. We can't even do cross product for a 4-dimensional vector because it's only defined for a 3-dimension. Okay, but we can do the dot product. Okay, now what I want you to do is imagine that the entry of this column vector is 0 everywhere except one place. Okay, and what will be the result? The result will be, for example, here it's a third position, it's non-zero, and otherwise it's 0. And the result will be the third value of the vector, third value of this vector, isn't it? So for example, if it's 2 3 5 6 7, then the answer is 5. Okay, and a vector similar to this, okay, we can have in the function space, okay, or a function vector space is known as a Dirac delta function. Okay, So the Dirac delta function we have already discussed. Okay, if it's going to be f2 of x is going to be a Dirac delta function del of x. Yeah, I'm just x minus p. Okay, and it's going to provide me only the value of f of x at x is equal to p. Okay, so it's going to be f of p. Okay, so like that you can associate this vectors in the form of functions. Okay, right. So I hope you have some better understanding on imagining the functions as a vector. Thank you.